Hey everybody, this is Alex Brissett from alexbrissettco.com, and this is my presentation, The World of Data. This is just kind of the summation of a lot of the research I've done the last few weeks into the big data world as I go to join that space. And the point is, whether you're a web developer, a data engineer, data analyst, anywhere in the programming space or data space, this is going to be a useful presentation to see, just to kind of get a big picture of how everything kind of connects, especially if you're just kind of new to these spaces. So if you're someone who's looking to become a data analyst, data engineer, web developer, etc., watching this to kind of get that big picture is going to be of value. So let's start. Okay, so let's just take a look at the big picture. So let's pretend we're talking about a company like Facebook. Okay, so Facebook, we have the Facebook application. Okay, now the Facebook application, there are a lot of interactions with the user. Okay, so if you're a web developer, you're building out this application, you're concerned with those transactions that the user undergoes being saved in a database somewhere, in a Postgres database, a Mongo database, a MySQL database, an Oracle database, whatever, a database. Maybe a graph database like a Neo4j or a ArangoDB, some sort of database. Okay, so those are referred to as database transactions. They're generally very simple in the sense that, like, I'm adding something, I'm editing something. It's usually like one record at a time, maybe a handful of records, but usually, again, you're making these small sort of transactions that reflect sort of user interactions with the application. On top of it, you may have logs. So you might log like how often, every time a user does this particular search or takes this particular action, start generating this metadata. So those transactions are all getting saved through your OLTP systems, your online transaction processing. So the idea here is you're not analyzing anything. You have interactions coming in and data's coming in, and you're saving these in these databases. Okay, transferring money from one bank account to another. Again, not analyzing. There's an actual like sort of transaction that's occurring. Now, what happens is that you will have different places to store the data. So a transactional database may not necessarily be the best place to also do your analysis from, especially when you're talking about large sets of data. Think about like a company like Netflix. Like I know I probably watch quite a bit of Netflix, and that's generating data on like what I chose, the genres and whatnot. On the same time, I'm getting data from them. So there's a lot of work that's undergoing in that transaction that you may need other places to kind of handle your analysis. So your OLAP systems, your online analytical processing. Okay, so again, this OLAP OLTP distinction is just sort of like a more high level concept of sort of what is the purpose of storing data here? What's the purpose of how we interact with data here? Okay, am I doing it because I'm trying to facilitate a transaction at the application customer level? Or am I doing this because I want to look at this data more holistically and do much larger scale queries and much larger scale processes to really kind of see if I can dig insights, analyze that data? So we may need to transform that data, because oftentimes data is sometimes not perfect. Maybe there was a weird outage, or some record didn't get completely there. Something's wrong with the data. Okay, or maybe we need to join things together. We have multiple pieces of data that really are more meaningful when they're put together, so we need to join them together. Maybe there's some columns that we need to rename. There's a bunch of different reasons why you may need to transform the data from your transactional systems to your analytical systems. And this process of doing that at any point is called ETL or ELT. So basically that just stands for exactly what you're doing: export, transfer, load. Okay, so I'm going to send the data out, I'm going to make any changes I want to make to it, and then load it to its new location. Or what I can do is I can export it, load it in the new location, and then transform it. But either way, there's a process by which that needs to happen. That's referred to as your ETL ELT process, which is part of your larger scale data pipeline, which is just the whole process from A to Z. Okay, and then again, here in the OLAP side, your consumers aren't customers, because your customers aren't analyzing your world data. They just want to, like, I want to go watch a movie, I want to go buy something on Amazon, I want to go like something on Facebook. But here you have people generally within the enterprise, within the business, who are looking at this data to see, again, looking for business insights, BI. So this can be done by taking that data and bringing it into platforms like Power BI and Tableau to create visualizations that can make certain trends very clear. It could be used to feed machine learning algorithms to help generate predictions and recommendations. It could be used to create reports, all sorts of different things, okay? But essentially, this is sort of the big picture. We have our transactional side of our data life, and then we have our analytical side of our data life. And the ETL process is kind of what bridges the two together. We'll talk more about like where these things get stored as the presentation goes. But on the transactional side, most of the time you're using probably like an SQL database of some sort, and most SQL databases and some NoSQL databases are what's called ACID compliant. And having a ACID compliant database just means you have to be worried, you're not necessarily worried about things going wrong in your day-to-day data transactions. Okay, because everything's kind of in its own little bucket. So the ACID stands for atomicity. Atomicity just means that like your transaction is do or die. Okay, in the sense that like, let's say a transaction is not just necessarily one query. So it might, like for example, to do what I want to do, I may have to go find something, then modify it, then update it. So then that'll get treated as one transaction. Okay, it might be multiple queries, but it's one transaction. And what's going to happen is that once it bundles something as a transaction, the atomicity guarantee, and you always find people having a hard time to say that, atomicity, what that guarantee does is basically says if anywhere along that pipeline something goes wrong, none of it happens. Okay, so you don't end up having like half-done transactions. The transaction either succeeds or it fails because it's part and parcel to each other. Okay, it's atomic. It's one big thing. Okay, you might have, if you're into like blockchain, you might have heard of like atomic transactions where you're technically converting one crypto to another. Okay, and they treat it as one big transaction, but really what's happening is you're selling one currency into an intermediary and then buying the other one, but it's treated as one big atomic transaction. So that way everything happens. So you don't get a half-done transaction. It's all basically everything gets confirmed on both sides of that transaction, and once everything is known that it will go through, then it goes through. Consistency. Okay, this is generally like in enforcing sort of consistency and integrity of the data. This is usually done through schemas. Okay, so by enforcing schemas, which can be enforced on write, which means, hey, if your data doesn't look like this coming in, it's not coming in here. It could be enforced on read, which means that, hey, when you pull data out, only the data that matches the schema comes out. There's different ways of doing that, but the idea is that it's that enforcement of schema that provides consistency to the data. Isolation. Okay, so the idea here is that you isolate transactions. So basically, like, changes the two concurrent transactions. If one makes changes, they're not necessarily going to be visible to this other transaction. Just so that way they don't accidentally trip over each other. So everything is isolated, so that way all these transactions, again, don't trip over each other. It'll come up with some sort of way to kind of coordinate all that and orchestrate all that. And then there's durability, the fact that this will save and persist, and that's going to have to deal more with like the actual physical storage of where it is and the fact that it's a database. But the idea is that you want these characteristics, ideally, to be worry-free. But again, some databases, in order to achieve things like speed, have to give up some of these things, and we'll kind of get more into that. But again, the goal is always to have all of these if possible. Okay, but there's trade-offs. Okay, so that's one issue with like what database you choose, and again, that could be on the transactional side, on the analytical side, but also when you're actually taking a look at your actual data and structuring your data. There's certain different things you can do to speed up or optimize your data, because again, it's not always just about speed. Is a tricky thing, because there's speed of when you read, okay, and then there's speed of when you write, how fast it takes me to write new data to the database, and there is, as I'll discuss, a trade-off between these two things that kind of help one do the other. Also, there's optimization of storage, where I'm not storing duplicative data, and not storing duplicative data has a second benefit of making sure that I don't end up having mismatching data, because since the more duplicates I have of things, the more chances of things aren't going to match up perfectly or not be consistent. And that's where normalization comes in. So normalization is like if I have like a chart and I realize like, hey, I have everyone organized by department, so I'm literally repeating the word marketing department, marketing department, marketing department. and then, accounting department, accounting department, accounting department. What I'll do is instead break those departments into a separate table and relate them. So basically, instead I'll say like ID1, ID2, ID1. So that way, in case like the department changes its name or other data about that department changes, I only have to change it in one place. It's not duplicative. But that does slow down. So while that optimizes storage and helps integrity, it can slow down read times, because having to join that data is more processing intensive than just having one big already existing data sheet that you can just pull out. So again, trade-offs. Then there's indexing. Okay, so basically, again, going back to that whole department deal. Okay, if I just say, hey, go find me everybody who works for the marketing department, the database is probably going to just go row by row and look to see if each row, and that whole issue of looking by row is also a problem in itself. That's solved by solutions I will discuss later. No spoilers. Okay, but what's going to happen is that you're going to end up looking through maybe many rows of accounting department and many rows of warehouse department before you actually get to the people in the marketing department, before the first person in the marketing department even shows up. So what indexing does is that if there's a column that you're going to be using in your queries a bit, what you can do is you can ask the database to index it. Different databases do this slightly differently, but the basic idea is that it'll create like a balanced tree structure. So imagine like instead of having to go through every record, basically I said, okay, well, there's these possibilities, and some of these are on this side and some of these are on this side. So you want to look for this, and it's on this side, and now we've just narrowed it down in half. And then maybe breaks it down further from there, and basically speeds up the query a whole bunch. Okay, an even simpler way of thinking about it is just thinking of it like an index in the back of a textbook. Okay, because I could go through every page and look for the topic that I'm looking for, or I could go to the back of the book, look up the topic I'm looking for, which tells me exactly which page it starts on, and then I can start my search there. And that's essentially how indexing works. Problem is that index is a separate data structure. It's a separate thing that's being referred to. So essentially what's going to happen is that while that will speed up your ability to read the data, it'll slow down your ability to write the data, because every time you write new data to the database, guess what? You got to go update this index. So that way that can still consistently yield results. Okay, similarly, there's an idea of views. Now, the plain old views is really just a way of taking a particular query and making it feel like a table. Okay, but you're not technically creating a new table. You're just saying, hey, whenever I query this pseudonym, I'm really querying the results of this query. Okay, and that's fine. That is convenient. It doesn't affect speed or write or anything like that. It's just a convenience that databases have. Materialized views, on the other hand, are something that can speed up your read time. So imagine you're looking through like 1 billion records, or even 1 million records. Okay, and really all you care about are the people in the marketing department. Okay, so wouldn't it be easier if you just have the people in the marketing department as their own thing? But you don't want to create a separate table, because again, you don't necessarily want to create duplicative data, because again, things start to not match up. So what a materialized view is, it's kind of somewhere in between. You are creating a copy of the data. So I can sit there and do a query of all the people in the marketing department, and then kind of make it this sort of side table. Okay, and I can query that materialized view instead, and that's going to be a lot faster. The benefit of materialized views, though, is like, with some sophistication, I can set it up that it will, as things get written to the database, we keep track of changes, and then periodically that materialized view gets refreshed. So that way it's constantly matching the original set of data. So I'll have this faster thing. I can query this faster subset of my data, but it's constant. But by mapping its sort of relationship by using like data logs and doing, periodic refreshes based on sort of our data needs, you can have something that speeds things up at a pretty fast clip. But again, it slows down write times, because now every time you need to write data, okay, you have to go update that data log, and then periodically then you have to go refresh the data. And then again, if you make the data refresh on every write, that's going to make it most of the date, but then again, that's just even slower write times. But you could set up a period of time like, hey, refreshes every minute or every hour or every day. But again, then there's going to be these periods of time in which the data is not consistent, where the materialized view doesn't match the raw data set. So there's a lot of decisions to be made there, but that's another way of speeding up. So I can create an index, which allows me to kind of speed up a search based on column. I can have materialized views allow me to create like a subset of my data that's quicker to query for certain queries. Although I have to actually actively say I want to query that materialized view. It's not going to be like, it's not going to know. Okay, and this is going to be important later. Cool. So that's like on the database side, and you're managing your transactional database or any database whatsoever. But now we're getting to the side where we want to move our data in for the data analysis portion. And there's a lot of things we got to ask ourselves when we're talking about a lot of data, because again, there might be multiple databases, there might be some data that's held in like CSV files, JSON files. There's all sorts of data all over the place that I need to kind of like coalesce and become something I can analyze. Okay, so I'll talk a little bit more about data warehouses and data lakes a little bit, but essentially, like, you have a couple different choices of where you're going to store your data. And essentially, you could go the data warehouse route, or you can go the data lake route, and we'll talk about the pros and cons of that in an upcoming slide. But in all of that, there's all sorts of considerations of what you're trying to solve with whichever route you go. You care about like storage. Okay, where is this data going to get stored? How do I organize that storage? Because again, what's going to happen is I may have like 1 million files, but they're really all one big data set. It's just that you break down to little files, and I need to be able to recognize them as a table. And that's why we have these like table formats that kind of keep track of sort of like that allows you to be able to break up the data into smaller chunks, okay, but still treat it as sort of one large distributed table, because generally you're not going to be able to fit all this data on one computer. So you're going to have to use some sort of distributed system, whether that's like cloud object storage or the Hadoop file storage system that allows you to distribute the data across many computers. So you'll need some sort of format that you can overlay on top of that to kind of keep track of like what files go together, what's your actual data look like. So here you have all these files, but how do those files really translate into data? Processing, things like originally Map Hadoop, which created the Hadoop file system, HDFS. They had a system called MapReduce, which you would, create these jobs that would, analyze each computer that has a little piece of your data, would then process those changes to your data, and then it would reduce them all into one big data set for a particular query or something like that. The only thing is that it would do those jobs directly to the disk, which it's slow. Okay, if you're writing directly to disk, which is fine for some jobs, not necessarily fine for others. So then Spark came along that does a lot of that same work, but does it in memory. Okay, and then you have other tools like Dremio Presto, which can be used to help process the data, pull in from data sources, and query them. So I'm just putting this all in sort of the processing category, even though some of these do very different things. Speed. Okay, so again, the question is like, how do we analyze the data? What's going to be our interface with processing the data? Then are things we can do to optimize speed, okay, such as using file formats like Parquet. This is where I mentioned like columnar stuff is going to matter. So the idea is that instead of looking at your data row by row, because if all I'm doing is I'm querying like who's in the marketing department, I don't need to look at all the other data like name, first name, last name, phone number, address. I don't need to go move through that data and look at that data on my way to figuring out which rows have the data that I want. So if you organize the data into columns, what I can do is I can just yank out the column that I'm searching for, go through the columns, kind of identify which indexes have the data I want, and then I can go back and pull those indexes out of all the other columns. So I can much quicker search through my data, and then hey, if I'm only needing two columns of data, then I can just yank out those 2 columns and ignore the rest, because everything has been organized as columns instead of rows of data. So Parquet is one columnar format for writing files to disk. Okay, so the actual files you save on your computer. And then Apache Arrow is a columnar format particularly for like in-memory processing. So now, okay, I load up that Parquet file. Now in my computer's memory, I also want to represent it as a column to really optimize the speed of which I can query and look through that data. And then there's data visualization. So I've stored the data somewhere, and we're able to organize it and process it, and we're able to do it fast, but I still need to kind of like create some sort of visual that makes it possible for me to like determine business insights and things like that. Okay, so that's these are the kind of questions you have when you're on the big data space and you're trying to determine what your data stack looks like. So this kind of helps paint a picture of sort of your options. Like I said, I was going to talk about data warehouse versus data lake in a moment. Okay, so traditionally what you would do is you would use a closed data architecture. Okay, you'd use a data warehouse. So essentially you would be collecting your data from your transactional sources. So again, your database for this and your database for that, and any other data that doesn't necessarily, that could be represented in a file like JSON, CSV, Parquet, etc. And then you would create your ETL pipeline to transform that data. And again, that can be an intense process depending on what you need. Because if you're using a data warehouse, basically the idea is that everything is sort of horizontal in the sense that like the same data warehouse, they're going to provide you with the storage. They have their own internal format of how they keep track of the data that's stored and how it relates to each other. And they're going to have their own processing engine, their own query engine. So how you process that data and analyze that data is all proprietary. Okay, and basically you can't really use anything outside the wall. So you're kind of in this walled garden. Now, Pro, like since all those things are tailored to each other, there's a, hypothetically they would work better together because they're tailored for each other. Okay, but you have to make sure that the data goes in there and gets transformed into their proprietary format in their proprietary way. So this can create like really sort of long, complicated ETL migration, having to develop these migration systems to migrate that data. Okay, and then on top of that, like if you want to use some of these other really cool tools that are out there using open data architecture, you kind of can't. You'd have to actually like make a copy of the data. And again, you make a copy of the data, what happens? You run into situations where you start having inconsistent data. Okay, duplicative data just leaves the room for trouble. Okay, so you have those issues, and on top of it, like you have to all of this. The way you set it up, you may still end up having to create copies, because what you'll do is you'll set up like data marts for different like departments. So like, hey, there's a data mart, which will be just the data that relates to the marketing department, a data mart for the accounting department, a data mart for that department. You set up all these sort of marts from the original data. And that could result in creating copies depending on how that particular data warehouse works. It's just, there's different issues that you can run into with that. But then basically you would then connect that to your favorite tools and generate your BI dashboards, machine learning, etc. Nowadays, you have a lot more open source technology, and a lot more of those open source technologies have been really tailored to work with each other and created intermediary formats to work with each other. Okay, particularly like Apache Arrow, that's really created like a standard way of representing data and then also with Apache Arrow Flight created uniform connectors that all these sort of open source tools can connect to each other more effectively, which really opens up the other route of using a data lake. It becomes a lot more practical today. Now, what does that mean? A data lake. A data lake just generally means it's like a lake where it's just a bunch of water and it's free flowing. In the sense, your data is free flowing. You're basically just using like something like the Hadoop file system, which is, imagine like hundreds, if not thousands, of computers coordinating data together and basically holding one big giant data set. And a little bit more complicated than that, or you could use object storage, like Amazon's S3 or Azure Data Lake or Google Cloud Dataproc. All of these places, it can be places where you can like store your data. It doesn't necessarily have to be, you don't have to like handle this whole ELT process up front. You can just have the data there. Okay. Although you may want to do some of that. And again, you can overlay it a table format that satisfies your needs the most. Okay, and run the big open source alternative here is Iceberg, because Iceberg is actually going to provide you some of those ACID features, which can be very difficult on a distributed data system. So one thing is you have one server with a database, that database can maintain itself. But what happens when you start talking about data being distributed across hundreds, thousands of computers? It becomes a lot harder to maintain those ACID parameters, and that's what Iceberg does a lot. Okay, to a great extent. So Iceberg's pretty cool in that regard. Okay, Hive is sort of like the OG table format, and basically doesn't it works and keeping track of what files are what, and then keeping track of them based on certain like dimensions like month, year, hour. But it was really like the later entrants like Delta Lake and Iceberg that really kind of provided a more robust feature set. So then there's like Delta Lake that connects very intimately with with Apache Spark. Well, Iceberg is can set up in a way that can really kind of connect with anything. Okay, then you can have your different processing and query engines. Okay, then there's things like Dremio, which takes huge advantage of things like Apache Arrow, Apache Aeroflight, takes advantage of Iceberg, and then also another thing called Project Nessie, which is a developing technology which is like Git but for data. So you can actually start creating versions of your data without necessarily creating copies of your data, and be able to do branches and merges. So essentially you can have the version management that you can have as a developer, but with your data, and not have the issue of having multiple copies. It's kind of like what used to exist before programmers had Git. We would upload stuff through FTP, and then what would happen is that somebody made their own version of the file, and they would just overwrite my file via FTP, and you'd end up with this whole mess. Git fixed all of that, and Project Nessie's aiming to do that for the data world. Okay, and so Dremio takes advantage of those technologies, allows you to kind of connect any of these storages. So in this case, the beauty of this is you don't need vendor lock-in. Okay, you don't need vendor lock-in because since you're using all different types of open source data technologies, it's not like, hey, if I use Dremio, I can't use Spark, and if I use Spark, I can't use Dremio, and so forth. Okay, I can store my data where I want and still use both. Okay, I can use Iceberg and still use Dremio and Spark. Basically you use the tool, and then as new tools come out, you can then use those tools. Okay, you're not locked into a box, and that's sort of like the big proposition of the new open data world. Okay, and if you haven't heard any of the talks by Dremio founder Tomer Shiran, I highly recommend listening to him. I really articulates this whole idea of the open data world in a very beautiful way. I highly recommend giving it a listen. I'll put a link to one in the video description. But yeah, so I mean that's kind of like the future, sort of like the big picture of the data world. Hopefully you found this interesting and enlightening, and understanding sort of like where data is and where it's going, and what's exciting about sort of again open technologies. And open technologies constantly disrupting things. I mean, you take a look at any space where open source has taken hold, it's led to a lot of innovation. It's led to a very consumer friendliness, in the sense of not pricing, ability to get innovation, access to alternatives, and things like that. So overall, lots of reason to be optimistic if you're a data professional. But also at the end of the day, that affects all of us individually, in the sense that better data means we can find solutions to problems that are real. Whether you think about like biomedical data that's going to be used to cure diseases, or financial data that's going to be used to help steward our resources better, and that's going to have like personal benefits, economic benefits, and all this stuff. And it's something we should all be very excited about. So hopefully you guys enjoyed this video. I'll see you all later. Have a great day and enjoy.